You wake up to a notification from your cloud provider, your API usage has spiked, and you've just burned 500 on a single refactoring task. This isn't a hypothetical nightmare. It is a common reality when using agentic workflows like Claude 3.5 Sonnet or GPT-4 for large-scale code migration. The trap lies in the context bloom. When an autonomous agent attempts to fix a production bug, it often pulls in entire directory trees to understand dependencies. If the agent gets stuck in a recursive reasoning loop constantly retrying a failing test case, it resends that massive context window over and over. Within minutes, you aren't just paying for the solution, you are paying for every failed thought the model had. In professional environments, ignoring this cost velocity can turn a productivity tool into a financial liability. We need to move past the cloud-only honeymoon phase and look at the hard numbers. By the end of this lecture, you will know exactly when to pull the plug on the cloud and move your inference to a local cluster. But first, we have to understand why this happens even to senior engineers. Teaser, the problem isn't just the price per token, it's how the models actually process your logic, which we'll deconstruct right now. To manage this, experienced teams don't just use LLMs. They build a decision framework based on return on investment, ROI. If you're building a simple CRUD app, paying for a 200K context window is overkill. A hybrid setup where a local 7B or 14B model handles initial boilerplate, syntax checking, and unit test generation, while a frontier model like Claude handles the final architectural glue is often the sweet spot. The goal is to reach a break-even point where the hardware investment for local inference pays for itself by reducing cloud API calls by 70% or more. However, this transition isn't free. It requires understanding quantization, VRAM limits, and the reality of local performance. We often see teams rushing to buy H100s without a clear plan, only to find their local models can't even follow a system prompt correctly. Question, is the local model really cheaper if it takes 5 attempts to produce one working function? I'll show you how to calculate that hidden labor cost in the next section. If you look at the leaderboards, models like Qwen 2.5 Coder or GLM4 seem to be breathing down the neck of GPT-4. They boast high human evil scores and impressive Python pass rates. But here is the catch. Benchmarks are static. In a real-world coding environment, you aren't just writing an isolated function for its palindrome. You are working with a legacy codebase, obscure internal libraries, and often comments written in Korean or other non-English languages. In my experience, while Qwen and GLM are incredible for their size, their reasoning density often drops when the prompt complexity increases. They might pass a benchmark test, but fail to understand a complex multi-file dependency in your actual terminal. When we compare theoretical score vs developer experience, DX, the gap is wider than most influencers suggest. Payoff now, let's look at the actual data where these local models start to break down under pressure. The most critical failure point for local models is the logic loop or reasoning hallucination. When you ask Claude 3.5 to refactor a class, it typically maintains a mental model of the entire object hierarchy. Local models, especially those under 30B parameters, tend to forget the system constraints or fail on tool calling. They might hallucinate a function that doesn't exist or get stuck repeating the same incorrect syntax because they lack the self-correction depth found in frontier models. This results in a logic spiral where the model confidently provides code that looks correct but fails silently at runtime. Understanding this limitation is the key to building a successful local pipeline. You don't use local models for architecting, you use them for execution. Payoff knowing exactly where the reasoning breaks is what allows us to set the break-even point. In the next chapter, we will dive into the 4-axis break-even calculation to determine if your specific project is ready to go local or if you should keep paying the cloud tax. In the field, I see so many developers jumping into local LLMs without looking at the VRAM bill first. To run 2026 tier models like Kimi K2 or GLM 5.2 at a level that doesn't make you want to pull your hair out, you aren't looking at a basic laptop. We are talking about the VRAM wall. A quantized 70B model requires at least 48 GB of VRAM to maintain logic integrity. If you're on a Mac, that's a Mac Studio with at least 64 GB or 96 GB of unified memory because the OS eats a chunk of it. On PC, a single RTX 4090 with 24 GB is actually a mid-tier setup now, often forcing you to use heavy 4-bit quantization that kills the model's reasoning during complex refactoring. You have to ask, is your hardware an asset or a space heater? If your model takes 30 seconds to breathe before typing a single line of Python, you've already lost the productivity race. But wait, is it just about the initial purchase price? Actually, the hidden tax of local setups is far more annoying than the sticker price. Question, do you know how much your electricity and cooling actually cost when running a 450W GPU for 10 hours a day? Let's do the cold, hard math that most local LLM enthusiasts ignore. A Claude Pro subscription is roughly $20 a month. Over 2 years, that's $480. A decent local rig capable of rivaling Claude's 3.5 Sonnet's coding speed and intelligence will set you back at least on a $3,500 to $5,000 in 2026. If we look at the 24-month amortization, your local setup costs you roughly $150 to $200 per month just in depreciation. Add the cost of electricity, especially if you're in a region with high utility rates and you're paying a massive premium for the privilege of hosting your own model. However, there is a crossover point. If you are an agency hitting the Claude API limits every single day, or if you're running automated agentic loops that consume 5 million tokens a week, the local model suddenly becomes free after month 6. It's a game of volume versus fixed cost. If you're just a solo dev writing 100 lines of code a day, sticking with Claude is mathematically superior. Payoff, but the financial break-even is only half the story. The real cost is measured in seconds per token. In my experience, the productivity break-even is the silent killer. Claude 3.5 Sonnet delivers code at roughly 60 to 80 tokens per second. It's almost instant. A local 70B model on a mid-range setup often chugs along at 8 to 12 tokens per second. If you are in a flow state and have to wait 15 seconds for the model to suggest a simple boilerplate fix, your brain context switches. You check your phone, you open a browser tab, and boom, your deep work is gone. To truly replace Claude for professional development, your local setup must hit a minimum of 30 tokens per second. Otherwise, you're paying thousands of dollars to become a slower developer. We call this the latency trap. People focus on the monthly $20, but they ignore the $100 per hour cost of their own wasted time while waiting for a local GPU to finish a thought. Teaser, but there's one area where speed doesn't matter as much as where the data lives. Let's talk about the workload mapping. Not all coding tasks are created equal. Local models in 2026, especially the Qwen and GLM series, have become incredibly proficient at mechanical coding. This includes things like writing unit tests, generating boilerplate, or converting a JSON schema into TypeScript interfaces. These are tasks where you don't need a PhD-level architect, you just need a tireless intern. For these, a local model is a 10-10 choice. However, when it comes to high-level architecture like deciding whether to move from a monolith to a specific event-driven microservice pattern, local models still trail behind Claude's reasoning. They tend to give generic textbook answers that don't consider the nuances of your specific legacy codebase. I use a hybrid approach, local for the grunt work and cloud for the brain work. A question, but if the local model is just for grunt work, is it worth the security risk of using the cloud for the rest? For enterprise developers, the break-even isn't about money, it's about compliance. If you're working in fintech, healthcare, or on a proprietary kernel, sending code snippets to an external API is often a fireable offense. In these scenarios, the cost of the local hardware is effectively zero compared to the cost of a data breach or a legal lawsuit. When we talk about moving to local inference, we have to clear a specific security checklist. Is your local environment truly air-gapped? Are your weights verified? Are you logging local queries for internal auditing? Many devs think local tool is safe, but if you're using an unvetted VS Code extension to talk to your local Llama instance, you might still be leaking metadata. True on-premise AI is a discipline, not just a hardware choice. Payoff: once the security barrier is cleared, you face the final technical hurdle, the context window myth. We see 128K context or even WEM context on local model spec sheets now. Don't believe the hype blindly. In practice, local inference engines like llama.cpp or VLM require massive amounts of VRAM just for the KV cache, the memory used to remember that long context. If you load a 100,000 token codebase into a local model, your 24GB GPU will OM, out of memory, before it even starts thinking, or it will use context shifting, which slows performance to a crawl. Furthermore, the needle in a haystack performance of local models like Qwen or GLM 5.2 often degrades faster than Claude's when the context is 70% to full. You'll find the model forgetting a function definition from the top of the file while trying to write a call at the bottom. Curiosity: so if the hardware and context are such traps, which models actually survived the 2026 benchmarks? In the next chapter, we look at the 2026 Model Showdown to see who actually wins the logic wars. In late 2025 and heading into 2026, the biggest failure developers face isn't picking a weak model, but picking one that hallucinates API signatures. You download Qwen 2.5 coder thinking it's a Claude killer, but then it fails on a simple pedantic V2 migration because it was overfitted on legacy V1 examples. In the field, we see Qwen 2.5 coder 32B excelling in pure algorithmic complexity, often outperforming GPT-4 in Python-specific optimizations. However, it lacks the common-sense logic for business rules that Claude 3.5 Sonnet possesses. If you are building a math-heavy engine or a data processing pipeline, Qwen is your local beast. But if your code relies on subtle architectural patterns, you'll find it struggling without heavy prompting. By the end of this chapter, you will know exactly which model to deploy for your specific tech stack. But first, let's see how it handles a complex async fast-to-byte refactor, the moment where most local models start to sweat. GLM 5.2 is the dark horse in the 2026 landscape. While others chase raw coding benchmarks, GLM has carved a niche in multilingual documentation and complex logical reasoning. In many real-world scenarios, your code isn't just about syntax, it's about explaining why a certain architectural decision was made. GLM 5.2 manages to bridge the gap between legacy Java systems and modern Go services with surprising clarity. In my experience, when you ask a local model to document a messy 1,000-line monolith file, GLM is the only one that doesn't lose the thread halfway through. It understands the intent better than Qwen. But here is the catch: GLM requires significantly more VRAM for its attention mechanism to stay sharp over long contexts. Is the extra hardware cost worth the better documentation? Let's look at the logic to memory ratio. Now, if you're an Apple Silicon user, Kimi K2 is likely your daily driver. In 2026, Kimi K2 has implemented a proprietary quantization kernel specifically for Apple's unified memory. While other models struggle with the latency of shared memory, Kimi K2 flies on an M3 or M4 Max. We are talking 45 to 50 tokens per second on a local machine that's faster than most cloud APIs. This makes it perfect for real-time autocomplete style agents that need to see your whole project structure. However, there's a trade-off. Kimi K2 is aggressive with its KV cache pruning. This means if you have a massive project with 50+ open files, it might start forgetting the context of your initial configuration file. This is a classic trap, speed over memory stability. But wait, does this speed actually translate to fewer bugs in production? The critical failure point for 90% of local LLM implementations is tool calling. Cloud models like Claude 3.5 Sonnet have been fine-tuned on millions of function calling traces, resulting in near-perfect JSON outputs. In contrast, local models like Qwen or GLM often fail the agentic test. They might hallucinate a required parameter or fail to escape a string correctly in a JSON block. If your local model is supposed to trigger a GitHub action or query a database, a single missing comma will crash your entire workflow. In production, we see a 12% higher failure rate in complex tool chains when using local models compared to cloud counterparts. This is where the break-even point usually breaks saving on API costs, but spending 10x more on debugging broken agent loops. But what if I told you that you could fix this with just a better system prompt? Local models are like highly skilled but incredibly literal-minded junior developers. If you don't constrain them, they will loop or start yapping about unrelated code. To get local models to behave like Claude, you need a highly structured system prompt. Forget you are a helpful assistant. You needed to define the exact output format, the allowed libraries, and a chain of thought requirement. By forcing the model to write the logic steps in comments before the code, you drastically reduce logic errors. I call this the constraint-first pattern. It prevents the model from jumping to a conclusion and failing halfway through a complex class definition. But even the best prompt can't save you if you choose the wrong quantization level. This is where most people lose the battle before it even starts. Let's talk about the 4-bit lie. Everyone wants to run a 70B parameter model on their 24GB RAM gaming card, so they use 4-bit GGUF quantization. In coding, this is a recipe for disaster. Unlike creative writing where a slight drop in precision doesn't matter in coding, a single bit flip can turn a greater than into a greater than or equal to, introducing a subtle off-by-1 error that takes hours to debug. My rule of thumb for production coding: never go below 6-bit for models under 30B parameters. EXL2 is generally faster on NVIDIA hardware, while GGUF is more flexible for Mac users. If you see your model consistently failing on complex rejects or nested loops, your quantization is likely too aggressive. This logic degradation is invisible until you hit a corner case. But which inference engine should you use to run these weights efficiently? Finally, your software stack matters just as much as your model choice. Ollama is the easy button, but for professional developers, it often lacks the fine-grained control over context window and GPU offloading. LM Studio is fantastic for testing different quantization levels side by side. However, if you are building an actual internal tool for your team, VLLM is the industry standard for 2026. It handles paged attention, which allows you to serve multiple developers from a single GPU without the out-of-memory crashes that plague Ollama. Choosing the right engine is about maximizing tokens per second per dollar. In the next chapter, I'm going to share some real battle stories, specific moments where these local setups saved a project, and moments where they spectacularly failed. You won't want to miss the production gotchas that no benchmark will ever tell you. Let's start with a disaster story. I was refactoring a legacy authentication module, trying to save on API costs by using a fine-tuned local model. The model suggested a library called FastAPI Security Enhanced v4. It looked professional, and the generated code used its classes perfectly. There was only one problem: that library doesn't exist. It was a complete hallucination. In the 2026 landscape, even the best local models like Qwen or GLM still struggle with truthfulness when they feel pressure to provide a solution for niche frameworks. If I had blindly committed that code, we would have introduced a massive security hole. Local models prioritize plausibility over accuracy more often than Claude does, especially during complex refactors where context is sparse. But wait, hallucinations aren't even the most immediate danger you'll face next. We need to talk about what happens to your physical hardware. The OOM, or out-of-memory nightmare, is the silent killer of local LLM adoption. Imagine you're in the middle of a flow state running a 72B parameter model locally. Open a large feature branch, and suddenly your IDE starts lagging. Then your entire system freezes. What happened? Your LLM just tried to ingest 10,000 lines of context for a refactor and spiked your VM beyond its 24GB limit. In 2026, despite better quantization techniques like GGUF or EXL2, the overhead is still real. If your local LLM crashes, it often takes your LSP and autocomplete down with it, effectively turning your high-tech ID into a basic notepad. This resource competition between your LLM and your build tools is a tax most teams forget to calculate. Is there a way to prevent this hardware meltdown? There is, and it involves a strategy called graceful degradation. To survive in production, you must implement a fallback system. Don't let your productivity depend on a single local process. The pro move is to set up a confidence-based rating system. When your local model returns a response with low log probability scores, or if it fails a basic linter check on the generated snippet, your IDE should automatically reroute that specific request to a cloud model like Claude 3.5. This ensures that even if your local hardware is struggling or the model is confused, your development loop remains unbroken. We use small supervisor scripts that monitor the health of the local inference server. If the local latency exceeds 5 seconds, we fail over to the cloud. This local-first cloud fallback architecture is the only way to maintain 99.9% uptime for your AI tools. But how do we decide which tasks go where in the first place? Let's look at the routing logic. Smart developers in 2026 don't choose between local or cloud, they use both simultaneously through a cost-aware router. Think of it like a load balancer for your brain. Simple tasks like write a unit test for this utility function or add comments to this file are routed to a fast, local Qwen 2.5 coder instance. This costs $0 and takes milliseconds. However, complex tasks involving multi-file architecture changes or security audits are automatically tagged as a high complexity and sent to Claude 3, 5, or 4. By using tools like LLM or custom middleware, you can drastically reduce your monthly bill. In my experience, about 70% of coding tasks are low-complexity boilerplate that local models handle perfectly. You're essentially hiring a local intern for the grunt work and saving the expensive consultant for the hard problems. But wait, what happens when you ask the same question twice? That's where semantic catching changes the game. The final piece of the 2026 production stack is the semantic catch. Unlike a traditional key-value catch, a semantic catch uses vector embeddings to understand if a new question is close enough to a previous one. If you ask, how do I center a div, and later ask way to center a div element, the catch recognizes the intent and returns the local result instantly without hitting the LLM again. We use local vector databases like Milvus or Qwen for this. This doesn't just save money, it reduces latency to sub-10 milliseconds for common queries. Over a month, this catch becomes your team's collective memory. If one developer solves a tricky bug with Claude, the whole team gets that knowledge for free locally through the cache. This is how you build a system that actually gets smarter and cheaper the more you use it. Now that we've seen the battle stories, are you ready for the final decision? In the next chapter, it'll give you the definitive 2026 strategy to pick your winner. Many teams rush into local LLM adoption because of the privacy buzzword without actually calculating the operational overhead. In actual production environments, I have seen teams spend tens of thousands on high-end GPUs only to find that their developers still prefer Claude 3.5 for complex architectural refactoring. Why? Because the successful strategy is not about total replacement, it is about strategic offloading. Use high-performance local models like Qwen or DeepSeek for high-volume, low-complexity tasks like unit test generation or boilerplate, while keeping the heavy lifting for the cloud giants. The failed pattern is trying to build a private GPT that mimics every feature of the cloud. You will end up with a maintenance nightmare and outdated weights within 3 months. Real senior engineers focus on the inference-to-value ratio. If you're not processing at least 5,000 tokens per developer per day, your local migration is likely a vanity project. But even with the right mindset, the hardware costs can be a trap. How do we know when it actually pays off? So, when do you actually pull the trigger on a local setup? By 2026, the break-even point has shifted significantly. We are looking at what I call the 30-month rule. If your monthly API bill for Claude or Gemini exceeds the amortized cost of a high-end local workstation, think dual RTX 50 series GPUs within 30 months, you are a prime candidate for migration. But it is not just about the hardware. You must factor in the context gap. Models like GLM or kimi are fantastic for specific Asian market nuances and Korean linguistic tokens. But if your codebase relies on niche frameworks, you need to verify if the local weights can handle the syntax without hallucinating. This checklist is your survival guide. Assess your daily token volume, your data sensitivity requirements, and most importantly, your team's ability to manage a production-grade inference stack. Hardware is just the foundation. The real question is whether the open-source ecosystem can actually keep up with the intelligence of cloud giants in the long run. Looking toward late 2026 and 2027, the landscape is splitting into 2 distinct paths. Cloud models will remain the kings of zero-shot reasoning, handling the complex architectural decisions that have never been seen before. However, the open-source roadmap is accelerating towards specialized mastery. We are seeing 70BB models that outperform GPT-4 in specific niches like Python optimization or advanced SQL generation. The local LLM trap will catch those who didn't plan for a hybrid architecture. The winners were the ones who treat local LLMs as specialist agents rather than general secretaries. Expect to see a world where your ID automatically switches between a local Qwen variant for real-time autocomplete and a cloud-based Claude for deep system design reviews. The gap is narrowing, but it's not closing entirely. It's diversifying. Now that we've mapped the future, let's look at what you need to do tomorrow morning to stay ahead of the curve. We have covered a lot of ground, from the technical limitations of local inference to the hard math of the break-even point. Your action plan for the 2026 landscape is simple. Start hybrid. Do not throw away your Claude subscription yet. Instead, set up a local proxy something like LLM and route your high-frequency, low-risk task to a local Qwen or Llama instance. Focus on building a private RAG pipeline for your internal documentation. That's where local LLMs truly shine without the risk of data leakage. Remember, being a senior engineer isn't about using the shiniest tool. It's about choosing the most efficient one for the business. Implement these 3 steps, audit your current token spend, benchmark a local model against your specific stack, and automate the routing. This marks the end of our journey into the local LLM trap. Use this knowledge to build faster, safer, and smarter than the rest of the industry. This is the final step in mastering your 2026 coding environment.